Sir, you can start, sir.
Okay, ma'am. Can you please make me the host of this meeting, ma'am? Yeah, thank you so much, ma'am. Good evening,
You're
students.
welcome.
Good evening, students.
Good evening, sir.
So, we have been discussing the concepts of current electricity in our previous classes. Today, we are going to continue our discussion on the same subject, that is the current electricity, and we are going to discuss the Wheatstone bridge now. Okay, the Wheatstone bridge we are going to discuss now. So first of all, let me draw the circuit of this Wheatstone bridge. After that, we shall continue our discussion. This is how a Wheatstone network looks like. Okay, so actually it is very symmetrical. Okay, it is in the shape of a diamond. Okay, like this. Okay, since I am drawing it in a manual way, it looks like a little bit asymmetrical. So you please never mind that, because the concept is actually the same. Okay. So this is the circuit of a Wheatstone bridge, and you are having resistances here. And here you are having another resistance. And here you will be having another resistance. Here you are having another resistance. Let me give name to these resistances as P, and here it is Q, and this resistance is R, and this resistance is S. Okay, these are the names given for these resistances, and this is a galvanometer. Okay, so it is represented in round shape. So here I am having a connection to a battery. This is the battery. It is represented in green color, and this is the positive terminal. This is the negative terminal. The EMF of this battery or cell is E, and I have the points A and this point B, this point as C, and this point as D. So this is the circuit of a Wheatstone bridge. You have four resistances P, Q, R, and S here. and you have to adjust the values of these resistances, okay, P, Q, R, and S, such that the current through this galvanometer is 0. That is represented by I suffix G. Okay, the current through the galvanometer should be set to 0. That means the points B and D here are at the same potential. That means there is no potential difference between this point B and this point D. Okay, so here you see this point B and this point D. When they are at the same potential, there is no difference in potential between these 2 points, okay, B and D. So in that case, current won't flow from this point B to G, okay. So you have to adjust the resistance values of all these P, Q, R, and S, so that the current through the galvanometer becomes 0. So now the current through the galvanometer, when it is 0, okay, when Ig equal to 0, you will be getting this condition, P by Q equal to R by S. This is the bridge balance condition, okay, and this is called the bridge balance condition. That means no current should flow through the galvanometer. This is called the bridge balance condition. So no current is flowing through the galvanometer. In that case, you will be having this P by Q equal to R by S. Okay. So this is the concept of a weak stone bridge. Okay. And what happens if P by Q is less than R by S? Okay. If this P by Q, if this P by Q is not equal to R by S and it is lesser than R by S, then what will happen? Current will flow from B to D. Okay, current will flow from B to D. Okay, if P by Q is lesser than R by S. So if P by Q is greater than R by S, what will happen? If P by Q is greater than R by S, what will happen? Current will flow from D to B. Okay, current will flow from D to B. And these conditions are very important for you when you solve numerical problems related to this Wheatstone bridge. So whenever you solve problems on Wheatstone bridge, okay, in that case, you may be asked to find out the direction of current flow in the Wheatstone bridge. So in those cases, this Wheatstone bridge balance condition and these conditions, P by Q less than R by S and P by Q greater than R by S. So all these concepts will be useful to you in solving the numerical problems. This is the concept of a Wheatstone bridge, and based on this Wheatstone bridge, you can have a meter bridge actually. So does anyone know about meter bridge? Can anyone tell me what is the meaning of, or what is the concept of this meter bridge? Yes, students, can anyone tell me what is the concept of a meter bridge?
So,
Yeah, tell me.
so a meter bridge is a device, sir, that is used to, sir, it is basically the same thing as this Wheatstone bridge, sir.
Yes.
But it's a practical version of this Wheatstone bridge, sir.
Absolutely right. You are right, Ajay Sariel. Actually, the meter bridge is actually the practical application of this Wheatstone bridge. Okay, so meter bridge is the practical application of this Wheatstone bridge. So what is the purpose of this meter bridge? Actually, whenever you have four resistances, okay, four resistances P, Q, R and S, and when you know the resistance of any three of these four resistances, then the fourth resistance can be calculated using the meter bridge. Okay, and meter bridge works on the principle of this bridge balance condition or the Wheatstone network. So here you will be having a 1 meter length wire, and you will be having this P by Q. Okay, P by Q as the resistance of the segments of that 1 meter wire. Okay, so these P and Q are actually the resistances of a particular segment of a 1 meter length wire, actually 1 meter long wire. So here you will be having a jockey, and using that jockey, actually you have to find the bridge balance condition or the balancing length. Okay, there also you will be having a galvanometer. When the jockey actually touches the wire and the galvanometer shows null deflection, then you can be sure that you have found out the balancing length. Okay, the balancing length is represented by the small letter L. Okay, so the balancing length is represented by small letter L. So in that case, P by Q equal to R by S, okay, according to Wheatstone network, and here it will be divided by 100 minus L. And what is the meaning of this L? L is actually the balancing length found out from the experiment. Okay, whenever you move the jockey over the wire, and at a particular point of contact on the wire, you will be finding that the galvanometer shows null deflection or zero deflection. So in that case, you have attained the bridge balance condition. Then you have to find out the balancing length value. Okay, since it is a 1 meter long wire, the remaining portion of the wire, you can find out the length. Actually, you can find out the length using 100 minus L. That is, overall it is 100 centimeter wire. So if it is 37 centimeter, for example, if L is 37 centimeter, the remaining portion of the length, the remaining portion of the wire has the length 100 minus 37. That will be 63 centimeter. So like that, you can find out the remaining portions, remaining segments length. Okay. So using this formula, P by Q equal to L divided by 100 minus L, you can find out the unknown resistance. Okay, you can find out the unknown resistance. So P by Q equal to L by 100 minus L, that will be equal to 100 R by S actually. Okay, so if any three of the resistances are known, the P and the Q and R, if it is known, then you can find out the value of this S using this condition. Okay, this is the concept of a meter bridge. Okay, so you may be getting some numerical problems based on this condition. Okay, right. And then example for a meter bridge, you can consider a potentiometer. Okay, so potentiometer is also one form of meter bridge. So using potentiometer, what you can do, you can find out the potential difference in a circuit. Okay, so using a potentiometer, you can find out the potential difference, or what you can do is you can compare the EMF of two cells. Okay, compare the EMF of two cells using this potentiometer. This device can be used to find out the compare the EMFs of two cells, and you can also find out the internal resistance of the cell. You can measure the internal resistance of a cell using this potentiometer. Okay, internal resistance you all know very well. So comparison of EMF of two cells and measuring the internal resistance of a cell. Both these things can be done using a potentiometer. Okay, then what is the concept of this potentiometer? It is same as that of a meter bridge. Okay, in a meter bridge you are having a 1 meter long wire. Okay, you are having a 1 meter long wire, but here in potentiometer what you are having? You are having actually 10 segments of wire. Okay, you are having 10 segments of wire, and each wire is 1 meter long. Okay, each wire is 1 meter long. So each wire is 1 meter long. So using this potentiometer, you can find out the balancing length. Okay, by connecting a cell, and the EMF of that cell is actually directly proportional to the balancing length. Okay, EMF of that cell is directly proportional to the balancing length, and this is the concept of a potentiometer. The EMF directly proportional to the balancing length. And using this concept, what you can do is you can compare the EMFs of two cells. Okay, how can you compare the EMFs of two cells? You can take out, two cells. Okay, first of all, you connect a cell of EMF E1 in the potentiometer, and you find out the corresponding balancing length. Then you remove that cell, and then you have to connect another cell of EMF E2, and you have to find out the corresponding balance length L2. So you can compare the EMF of these two cells using this relation. E1 by E2 equal to L1 by L2. This is the relation, or this is the expression used to compare the EMFs of two different cells using a potentiometer. Okay. So this is how you can find out the ratio of the EMFs of two cells using a potentiometer, and it's one of the applications of this potentiometer. Okay. So then what you can do, you can also measure the internal resistance of a cell. Okay, internal resistance of a cell can be measured using this potentiometer. So what is the equation for finding out the internal resistance? So R equal to E by V minus 1. E by V minus 1 into capital S. Okay, into capital S. So capital S is that resistance box. Okay, which you include in the potentiometer. So R equal to E by V minus 1 into S. So using this relation, you can find out the internal resistance. Okay, this E by V means in the absence of an external resistance, you can find out the balancing length that is given by L1, and when you include the external resistance, you can find out the balancing length that is represented as L2. Okay, so R is equal to L1 by L2 minus 1 into S. S is actually the resistance box. Okay, so I am just telling you the concepts of this potentiometer. Okay, so using these conditions, you may have to solve the numerical problems and find out the internal resistance of a cell. Okay, using a potentiometer, and I am just telling the concepts now. So when we solve some numerical problems based on these concepts, you will understand it very well. Okay. So R equal to E by V minus 1 into S. So how you can find out E by V? That is by finding the balancing length. So initially, when you have just the cell in the circuit, the balancing length is L1, and when you have an external resistance included in that, you will be having a different balancing length that is represented as L2. Okay, so small r equal to L1 by L2 minus 1 into S. So this is the concept of finding the internal resistance of a cell using a potentiometer. Okay. And now, do you all know about the concept of galvanometer? Can anyone tell me what is meant by galvanometer? Whatever you know about that, you can. Yes, tell me.
So it's basically a device which is used to detect currents and even measure very small amount of current, sir.
Yeah, absolutely right. So galvanometer is a device, okay, used for measuring small amount of current in a circuit. So a device for measuring small amount of current. Small amount of current. This is what a galvanometer is all about. Okay, the device for measuring small amount of current. So here you will be having a pointer. Okay, that pointer will show deflection corresponding to the numerical value of current. So actually, a galvanometer is a highly sensitive instrument, and it gives full-scale deflection for even very small values of currents of the order of 10 milliampere. So high strength currents cannot be measured with the help of a galvanometer directly. Okay. So what is the problem is it is a very sensitive instrument, and such a sensitive instrument cannot be used to measure some high currents, okay, because it gives full scale deflection even for a 10 milliampere current, and whenever you want to measure currents of value higher than this 10 milliampere, then you can't use the galvanometer directly as such. For that, what you can do is you can convert a galvanometer into ammeter. Okay, you can convert a galvanometer into ammeter, and then you can measure the current. Okay, so conversion of galvanometer into ammeter. Conversion of galvanometer into ammeter. How you can do this actually? How you can convert a galvanometer into ammeter? Okay, for that let me draw a circuit. Okay, so that you can understand it easily. And this is a galvanometer. Okay, and the resistance of the galvanometer is represented as capital G. Okay, and here I have this galvanometer, and here the total current enters this galvanometer as I. Okay, and what I have to do is I have to connect a low resistance in parallel. Okay, that low resistance is called shunt resistance. That low resistance should be connected in parallel to the galvanometer, and the current flowing through the galvanometer is represented as I suffix G. Okay, so the total current is I. The Ig amount of current flows through the galvanometer, so the remaining current is I minus Ig. So that I minus Ig actually flows through this shunt resistance, and the entire combination, a galvanometer with a low resistance in parallel connected with it, so it is called an ammeter. Okay, the low resistance in parallel. Okay, so a galvanometer can be converted into ammeter by connecting low resistance in parallel. Okay, low resistance in parallel. So this is how you can convert a galvanometer into ammeter. And what should be the value of this shunt resistance? Okay, how can you calculate the value of this shunt resistance? For that, there is a formula. So S is equal to Ig divided by I minus Ig multiplied by G. Okay, multiplied by G. So S equal to Ig divided by I minus Ig multiplied by G. That means the shunt resistance, the value of shunt resistance you can calculate using this equation, Ig divided by I minus Ig into G. G is the galvanometer resistance, and using this formula or using this equation, you can find out the value of the shunt resistance that should be connected in parallel with the galvanometer to convert it into ammeter. Okay. So this is the concept of a galvanometer to ammeter, conversion of galvanometer to ammeter. Okay. Do you all understand this concept, students? Conversion of galvanometer into ammeter.
Yes, sir.
Yes. So thanks for your response. And now a galvanometer can be converted into ammeter, and it can be used for measuring currents. At the same time, a galvanometer can also be converted into voltmeter for measuring the potential difference in a circuit. Okay. So you can also use the galvanometer as a voltmeter by converting it. Okay. So conversion of galvanometer into voltmeter. How can you convert a galvanometer into voltmeter? Does anyone know about this? If you know about this, you can tell me. How can you convert a galvanometer into voltmeter?
Sir,
Yes, tell me.
sir, by connecting a very high resistor, sir, very high resistance resistor, sir, in series with a galvanometer, sir.
Yes, absolutely right. You have to connect a high resistance in series. Okay, exactly the opposite scenario. So here you have to actually connect a low resistance in parallel with the galvanometer to convert it into ammeter. But here what you have to do, you have to connect a high resistance. Okay, you have to connect a high resistance in series with the galvanometer. This is the galvanometer, and here you have the high resistance. High resistance, and this is the galvanometer. Okay, so galvanometer connected in series with this high resistance. It constitutes a voltmeter. Okay, it constitutes a voltmeter, and the total potential difference. Okay, the total potential difference across this arrangement. Okay, the total potential difference across this arrangement is actually capital V. Okay, the total potential difference across this arrangement is capital V. Okay, how you can find out the value of this high resistance that should be connected in series with the galvanometer? For that, you have to use this equation, R equal to V divided by Ig. Okay, What is Ig? Ig is actually the current flowing through this circuit. Okay, since it is a series combination, the current is same across the galvanometer and also the high resistance. The current is same. So R equal to V by Ig minus G. Okay. So in this way, you can find out the value of the high resistance that should be connected in series. So how you can convert a galvanometer into a voltmeter? By connecting a high resistance in series. Okay. So by connecting a high resistance in series, you can convert the galvanometer into voltmeter, and the value you can find out using this equation. Do you all understand this concept, students? Anyone have any doubt here?
No doubt, sir.
Yeah. So the next concept which we are going to discuss is electrical energy and power. Okay, we shall discuss something regarding that. Electrical energy and power. Electrical energy and power. So what is meant by electrical energy and power? Okay. So whenever you connect a battery to a conductor, okay, whenever you connect a battery to a conductor, what happens? The battery supplies the potential difference across the conductor or across the wire. Okay, whenever you take a wire and you apply a potential difference capital V by connecting a battery to the circuit or to the wire, then what will happen? Electrons are actually accelerated in the process inside the wire, and they actually move forward with a common drift velocity, and in this process they collide with the other positive ions in the conductor, and due to this what happens is there will be some loss of energy, and that loss of energy appears as heat in the conductor. Okay, so actually what is happening here is the battery supplies actually the energy. Okay, the battery supplies the energy for the electrons to move forward, and the electrons carry the energy, and in the process of moving they collide with the positive ions, which leads to the dissipation of heat. So in this way, what happens is the electrical energy supplied by the battery is converted into heat. Okay, so that is called heating effect of current. Okay, that is called heating effect of current. So what happens actually is the battery or the source. Okay, the battery or the source does some work to move the charges through a potential difference V. Okay, so in general, the work done to move a charge Q in a potential difference is given by W equal to Q into V. Okay, this is the work done. This is the work done to move a charge Q. Okay, this is the work done to move a charge Q through the potential difference V. Through the potential difference V. So this work is actually done by the battery. So W equal to Q into V, and we all know very well Q is nothing but current into time. Okay, charge is nothing but current into time. So substituting this Q in this relation, you will be getting W equal to IT into V. Okay, IT into V, and this work done is actually converted into electrical energy. So H equal to ITV or VI H equal to VIT, and we can apply the equivalent of this V, that is V equal to I by R, okay, I by R into I into T. V equal to IR actually, okay, this is V equal to I into R, so V equal to I into R into IT, that will be H equal to I square RT. This is the heat energy generated in the conductor. So this is called the Joule's law of heating actually. H equal to I squared RT, and this can be also represented as H equal to I can be represented as V by R. So V by R the whole square into R into T. So H is equal to V squared by R into T. Okay. So this is the heat energy applied by the battery. Okay. So H equal to I squared RT, heat energy or electrical energy. So then what is the meaning of electric power? Okay. Electric power is actually the rate of doing work or the rate of flow of energy. Okay. So that is energy divided by time. So here you have the energy, that is I squared RT. So I squared RT divided by T. So power will be equal to P equal to I squared into R. Okay, P equal to I squared into R. The electric power can be calculated using this equation and I squared R, and we can also put the other forms as well. Okay. So this energy you can consider it here V squared by R. So P equal to VI. All these equations you can use for finding the power. Okay, electrical power. So P equal to VI. This is another equation which you can use, or P equal to V squared by R. This equation also you can find use to find out the power, electric power. Okay. So these are the formula or the equations for electrical energy and electrical power. Okay. Second, please. I'll be back. Yes, now we will be considering the concept of series combination or parallel combination of this electrical power. Okay, series combination or parallel combination of this electrical power we shall consider now. So series combination. Series combination of power. So series combination of power means actually For an example, you can consider that you are having bulbs of different power. Okay, actually in our households we use electric bulbs of different power, and you can consider that you are actually connecting bulbs of different power in a circuit. Whenever I tell you that I am connecting this power in this circuit, what I actually mean is that I am connecting a bulb. Okay, for an example, you can consider that actually I am connecting a bulb here. So what will happen if we connect many powers in a series combination, or for example many bulbs? Okay, we have already discussed the series and parallel combination of resistances and capacitances. So on these lines, actually we can consider here the series and parallel combination of power. Okay, so here you can consider this. So this is a battery. We are having different powers. Okay, different powers means different bulbs. Different bulbs will have different resistance. So different resistances here. So this is a bulb having power P1. This is a bulb having power P2. Okay, power P1, P2, and P3. Okay, and this is the battery supplying a potential difference V. Since it is the series combination, the potential difference across the different bulbs, okay, the potential across the different bulbs, okay, will be different. So here there will be different potential drops. Okay, different potential drops across the different bulbs. So what is the total power in this case? When you have different powers connected in series, what is the total power in this case? The total power is given by this equation. I am writing it here. Of course, you have derivation for this, but I am actually writing the final expression. So 1 by Ps equal to 1 by P1 plus 1 by P2 plus 1 by P3. Okay. When you have different powers connected in series, then the total power in this circuit is given by 1 by Ps equal to 1 by P1 plus 1 by P2 plus 1 by P3. Okay. If you have n bulbs connected in series, okay, if you have n bulbs connected in series, then what is the corresponding equation? 1 by Ps equal to 1 by P1 plus 1 by P2 plus 1 by P3, and up to you will be having n bulbs, so 1 by P suffix n. Okay, so in this case you will be having the total power like this. And now I am considering a scenario in which all the bulbs have the same power. Okay, all the bulbs have the same power. In that case, what will happen? If all the bulbs have same power, okay, and that is represented by the letter P, then 1 by P S is equal to 1 by P plus 1 by P plus 1 by P, like that it goes on. So that will be n by P. Okay, n number of times. So 1 by Ps equal to n by P. So what is the formula for finding the Ps? Ps equal to P by n. Okay, Ps equal to P by n. So when all the bulbs have same power, you have to use this equation to find out the total power in series. So when you connect different bulbs, okay, when you connect different bulbs in series like this, what will happen to the intensity or the brightness of the powers or of the bulbs? Okay, what will happen to the brightness of the bulbs when you connect all the bulbs in series like this? Okay, so here all bulbs will glow with power lesser than the respective rated power. Okay, since you actually have to divide the power, okay, you have to actually divide the power by total number n. What will happen? The total power decreases, so all bulbs will glow with power lesser than the respective rated power. So the bulbs will glow with lesser power, okay, with lesser power than the rated power in series combination than their rated power. And in a series combination, what is the other point you have to keep it in mind? That is a bulb with least rated power. Okay, a bulb with least rated power will be most bright. Okay, will be most bright. And vice versa. And vice versa. So whenever you have a bulb with different powers, okay, the bulb with the least rated power will be most bright in a series combination. And it is vice versa also. Whatever bulb has a highest rated power, that the brightness of that bulb will be very less in a series combination. Okay. So these are the characteristics of a series combination of power. In numerical problems, you may be asked which bulb will glow brighter and which bulb will glow dim. Okay, like that you may be asked questions during your examination. In that case, you must be able to answer. Okay, using these characteristic features of a series combination of power. Okay, fine. Then we will be discussing the parallel combination of power or parallel combination of bulbs. Okay, now we shall discuss that concept. So parallel combination of power, that is nothing but bulbs. Okay, parallel combination of power or parallel combination of bulbs. So here you are having a parallel combination here you are having a battery. and here you are having the different bulbs, and of course I am using a different color to represent the resistances or the bulbs. Okay, so this is P1, this is P2, and this is P3, and the battery supplies a potential difference of V. So in this case, what is the total power? Okay, what is the total power of this circuit? That will be P equal to P1 plus P2 plus P3. Okay, P equal to P1 plus P2 plus P3. And if you have n bulbs in parallel, okay, if you have n bulbs in parallel, then P is equal to P1 plus P2 plus P3 up to Pn. Okay, up to Pn. So if you have the powers of all these bulbs equal, okay, that means if P1 equal to P2 equal to P3, Pn is equal to P. In that case, what is the total power? P equal to N into P. Okay, P equal to N into P. So in this case, you can observe that the total power of the circuit actually increases. Okay, it is n times the power of a single bulb. That means when you connect all the bulbs in parallel, then the total power of the circuit increases. Okay, and moreover, all the bulbs will glow with their respective rated power. If P1 is not equal to P2, not equal to P3. Okay, if the power of all the bulbs are same, then the total power actually increases. P equal to N into P, the total power. Okay, so here all bulbs will glow with their respective rated power. So that thing you need to understand here, and here a bulb with lower resistance actually or the higher power, okay, will draw larger current. So usually in households, okay, we actually connect all the bulbs in parallel. Okay, in household circuit, you know very well that all the instruments are connected in parallel. Okay, there is no series circuits in our households. So all the bulbs and of course all the other instruments are connected in parallel. Okay, so here in the parallel combination of bulbs, a bulb with higher power will draw larger current. Okay, a bulb with higher power will draw a larger current in case of parallel combination. So a bulb with larger power will draw larger current, or higher power will draw a larger current. Okay, so a bulb with higher power, it will be drawing larger current. Okay, that's why whenever you use bulbs with very high power, okay, in your households, because in your households you actually use a parallel combination. Okay, so whenever you use bulb with higher power, for example a 40 watt, 80 watt, okay, like that, whenever you use a bulb with higher power in the parallel circuit, it draws a larger current, and it will lead to an increase in the electricity bill. Okay, it leads to an increase in the electricity bill for your household. So This is the reason a bulb with higher power actually draws larger current, okay, in a parallel combination. So, in series combination of bulbs, actually bulbs of greater wattage actually glow less brightly, as we have already discussed that. So, all these things you need to keep in mind when you solve the numerical problems, okay? And these are the things which we have discussed today, and in our next class we will solve the numerical problems in current electricity, okay? We will be discussing some numerical problems, some important numerical problems in current electricity in our next class, okay? So after that discussion, I will be giving you a test on current electricity, okay? So you will be given a set of 15 questions as usual, multiple choice questions. Once we complete our next class, okay. So after that, you have to write the test on this current electricity chapter, and you have to do the regular division actually. Then only you will be able to solve the numerical problems easily. Okay, fine. If you have any doubts on the concepts which we have discussed today up to this point, do you have any doubt on the concepts which we have discussed today?
No, sir.
Okay. In that case, thank you so much for joining the session, and do the regular revision, and in our next class we will be solving the numerical problems as well. So thank you so much for joining the session, students. Let us discuss the problems in our next class. Thank you so much.
Thank you, sir.
Thank you.